Hey guys, welcome back. Today we're going to be talking about rate of change. As our learning target, we're going to determine rate of change and relate it to slope as well as the context of the problem. To be successful in this, you're going to be able to calculate slope from tables, graphs, equations, or contexts, or you should be able to identify rate of change as a synonym for slope. So let's take a look at the key idea behind using the word rate of change. Like I said, they really are synonyms. So I have slope is the same thing. Oops, sorry, my pen's going crazy here. Okay, slope is the same thing as rate of change. They are equal. If you need, circle that, write that down somewhere. They mean the exact same thing. If you're asked for slope, they really mean rate of change. If they ask for rate of change, they really mean slope. I think of rate of change as being like the real life version of slope. So if you say slope, you could be talking about just a plain old graph without any real life connection. But if you say rate of change, there should be a real life connection, which if we think about slope, it's still vertical change over horizontal change, also known as rise over run. So if you get a question that asks for, say, the rate of change of this graph right here, I would still think of rate of change as slope or rise over run. So the rise here is 6 and the run here is 8. I would write my ratio, rate of change is equal to 6 over 8. And then I would also remember that any fraction I ever write, I should always try to reduce, and both 6 and 8 are both divisible by 2. So the rate of change of the triangle that is in my little square right here is 3/4. Okay, so just like we did slope, it's the same exact practice, only this time we're calling it rate of change, and we may need to connect it to a real life situation. All right, so in our first example, it says find the rate of change of the linear function that models the height of the zip line. Now, we're going to be talking about what it means to be a function in a few more lessons. Don't worry about the fact that it says function right there. In fact, if you want, you can change the word function and cross that out and make it say linear equation. Okay, because right now they really mean the same thing, and in another lesson we will specify what a function is. So I'm gonna look at my graph here, and I'm gonna figure out my rate of change. Now, rate of change is the change in the y over the change in the x, just like slope. So we're going to be looking for rate of change. I want to know how the vertical distance is changing as the horizontal distance is changing. So let's think about this zip liner. I want to know his rate of change, meaning how many feet is he descending per feet that he travels forward. So if he travels forward 50 feet, how far did he fall? That's going to be what our rate of change represents here. So I'm going to make my slope triangle connecting the first point where the zip liner starts and the end point where the zip liner ends. So I'm just going to draw my triangle here, and I'm going to zoom in a little bit. My picture is a little small. Okay, so I'm going to go from here. I'm going to fall down this much, and then I'm going to run all the way across, creating my slope triangle. Now, some of you may look at the grid and say, okay, this is 1, 2 units, and label that 2. But technically, it's not 2 units. You need to think about how far the zip liner actually fell. So to go from 250 to 200, he actually fell 50 feet. Remember, height is in feet. So I'm going to label this rise, or should I say fall, as -50. Again, since we're falling, we have to draw the line downwards in order to go from point to point. He fell 50 feet. So I'm going to write that as a -50 feet. Now, he is traveling in a positive direction. He's traveling to the right, and I want to know how many units that is. Well, he goes from 0 okay, 0 feet from the platform, to this would be labeled 300 feet, this tick mark right here. So he goes from 0 to 300. So this distance is not just counting the tick marks. Please don't do that. Okay, you want to actually figure out how many feet he traveled across. And from 0 to 300, that's 300 feet. So now that I've interpreted the rise and the run in the context of the problem, true to the graph, I can create the ratio that represents this slope. Or I should say the rate of change. We're talking about rate of change. I should use my synonym. So rate of change is equal to, and since I'm calling it rate of change, I'm going to put units on my rise and run. I really do feel rate of change is the real life version of slope. So I have a rise or a fall of 50 feet. I'm going to write feet. So negative 50 feet over 300 feet. So that can be interpreted as, for every 50 feet he falls, he travels 300 feet towards the platform. Alright, so this slide is really just a review of what I've already gone over. It's just emphasizing that rate of change is a synonym for slope, because this is what we've always written for slope in the past few days. So they just give us another example in the graph showing the rise divided by the run, or the vertical change over the horizontal change, and that reducing down to 2, because the 6 units over the 3 units reduces down to 2. Now, if you look at the equation of this line, they point out that the 2 in the equation is the rate of change. Just like I had mentioned before, we're not going to really pay attention to what's being added. We're just going to focus right now on what is multiplying the x. So the number that is multiplying the x value. That's what we want to focus on as calling slope, rate of change, or the multiplier. And that's going to be in the form, right now we're going with y equals mx. Okay, we're not doing the plus b yet, but that is going to come. So I want to be able to make sure you guys understand that m is the multiplier, the number that multiplies x, also known as slope, also known as rate of change. Again, rate of change is really like the real life version. Okay, so I'm just writing down, pointing to rate of change, saying that it's the real life version of multiplier or slope. So let's keep applying this idea to example 2. It says, identify the equation of each linear function shown at the right, then state the rate of change of the function. They also give us some equation choices, so they gave us some options right here. In all of those options, I want you to note what the rate of change is in each of them. And really, I just want you guys to notice it's always going to be the number that's multiplying x. So the rate of change in the first equation is 3. Let me get a little smaller of a pen here. Okay, 3. I don't know why my pen size isn't changing. Get a little bit smaller, see if that helps. Okay, and the rate of change in the second equation is -3. The rate of change in the third equation is 1/3, and the rate of change in the fourth is 3. So let's try to figure out what the rates of changes are in both this graph and table, and then I can figure out the equation. I think that would be the best order to go in. So let's examine the graph first. Let's look at the rise and the run so that we can figure the rate of change. The first thing we need to do is highlight integer value points. Again, we need to be looking where the blue line crosses over 2 grid lines. So here's an integer value point, here's another integer value point, and here's another integer value point. now from each of these points, I should be able to calculate the rise and run. It doesn't matter which 2 points you choose to go from, just choose any 2 points. So let's start at the leftmost point and just go to the middle point. There's my up and down, or my rise. Here's my left and right, or my run. So let's count the units now. 1, 2, 3. That's a rise of 3 and a run of 1. If I were to create my ratio now, I would write rise 3, run 1. I could even write that just as 3. So now I know, just looking at my equation choices, the only equation that has a rate of change is y, or a rate of change of 3 is y equals 3x plus 3. Now let's try the table. When we look at the table, we need to notice how the x's are changing and how the y's are changing. Again, the slope formula, or the rate of change formula, is the change in y over the change in x. Well, let's try to see how the y's are changing. From this point to this point, we had to add 2/3. From this point to this point, we had to add another 2/3. So it seems like the y's are changing by a positive 2/3. Let's notice now how the x's are changing. From this point to this point, we had to add 2. From this point to this point, we also have to add 2. So it seems like the rate of change for the x's is to add 2, and the rate of change for the y's is to add 2/3. So let's write that as a ratio. We may need to simplify it a bit though. So I'm going to write it a little bit below the box. I have my rise is 2/3. There we go, that's better. My rise here is 2/3, but I want to put that over the run, which is 2. So now we have to recall some fraction operations. So I'm going to write this a little bit different. Instead of dividing the fraction, you can change this into multiplication. So what is 2/3 times the reciprocal of 2, which is 1/2? Well, if you were to type 2/3 times 1/2 into your calculator, that's going to equal 1/3. Your calculator may have even spit out 0.3 repeating. That's the same thing as saying 1/3. So now I can go over to my equation choices, and I can see this equation right here is the only one that has the rate of change of 1/3. So the equation for the table must be y equals 1/3 x. All right, so we got one more example here. It says an employee at a candle making company collected data about the burn time of a new candle. Find the rate of change of the candle's height between 1 hour and hour 4. What does the rate of change mean in this situation? So they've created the table. They've also highlighted the 2 points that they want us to use. So we're going to use our slope formula here because rate of change is the same as slope. Rate of change is equal to slope, and slope is equal to the formula y2 minus y1 over x2 minus x1. So I'm going to go to my table and I'm going to actually label each of the points x1, y1, x2, and y2. So the columns, this is going to be the x column and this is going to be the y column. Anytime you look at a table, the first column should always be x and the second should always be y. So I'm going to label my x's first. So and it really doesn't matter which one is the first point and which one is the second point. I'm just going to go from top to bottom. So this is going to be x1 and this one's going to be x2. This one's going to be y1 and this one's going to be y2. whatever you do, just make sure if it's in the same row, then they have to have the same sub number. So if you label this one x1, then this one has to be y1. You can't switch them around. So now I'm going to go ahead and plug into my formula. y2 is equal to 13. y1 is equal to 22. x2 is 4. And x1 is 1. So now I'm ready to simplify my formula. 13 minus 22. I'm going to grab my calculator. I think you guys should too. Don't rely just on mental math. We're not that great at integers. Type in 13 minus 22. That gives me negative 9. Even if you feel you can do it in your head, just double check in the calculator. And then 4 minus 1 is 3. Make sure, whatever you do, every time you see a fraction, you should also reduce. Negative 9 divided by 3 is negative 3. So the slope of this situation, or the rate of change of how a candle burns, is going to be negative 3. We should definitely interpret this in the context of the situation. So 3, or negative 3 over 1. The 3 represents the rise. The rise represents candle height in centimeters. So negative 3 represents the height. So I would say, to interpret this in real life terms, I would say the candle loses, for that negative symbol, loses 3 centimeters for every, now the x is 1, and the x represented how many hours the candle had been burning. So I'm going to say for every 1 hour. That's my answer to this question in real life terms. So when it says find the rate of change of the candle's height between hour 1 and hour 4, we did that. The rate of change is 3 centimeters for every hour between hour 1 and hour 4. In fact, this rate of change would be the same no matter what 2 points you decided to do the slope formula in.
The way I would